So we have sorted list of numbers, but there's also shifted. So sorted order is like this: 1, 2, 3, 4, 5, and then they are shift left by some value like 3, 4, 5, 1, 2. And the goal is to find the smallest value. This is 1. And we have to do this in logarithm of n time complexity. Space complexity is 1. So the solution is the first brainless solution is just handful craft. Like invent the binary search from scratch. It would be painful, but it's doable. So we have low, high indexes. Then we have some middle pointer. And then we have to compare, like if it's normal situation or if it's shifted situation. So if it's shifted situation, the low would be bigger than high. And then we have to do the adjustment, and to make the adjustment we have to analyze again. In my solution that was accepted, I used comparison with low and mid, and if low is less than mid, then the first part is sorted, then we can go to the next of the mid. So let's look at the solution. This is a handcrafted solution. I use some brainless logic and invented binary search from scratch. So this is a custom check, then we check again, and then do the adjustments. So if low is bigger than mid, then we have inversion, and then we move the high pointer to the mid. Otherwise we move low pointer to the next, because the first prefix is sorted. Now let's think about it in an unexpected way. So it takes some brain cell, and unfortunately I don't have one because I used AI to find the solution. But the idea is that we actually have a good heuristic, like false, 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 is 3 numbers false, and then 2 numbers true. Basically this becomes a super simple binary search with just a 1 shift from 0 to 1, and the idea is to compare the latest rightmost value. So for these 3 numbers, this is bigger than last value. So 3 is bigger than 2, 4 is bigger than 2, and 5 is bigger than 2. And for the last 2 is smaller, so 1 is smaller than 2, and 2 is 2, so not relevant. So basically we have to compare with, if it's smaller than last, just a simple check, and then we can use simple binary search. And now let's look at the solution. For the simple binary search we can use the built-in functions like partition point in Rust, just x bigger. Okay, so I kind of misrepresented it by it's not very painful mistake. So, and this is a Kotlin one, as list binary search bigger than last, go to the left. So that's it for today.